All right, our second speaker is Hossein Dehghani. He's a postdoctoral research associate at UMD and JQI. During the last few years at UMD, he has been working on different problems in the intersection of quantum many-body physics and quantum information, including quantum dynamics, quantum simulation, and quantum error correction. In this talk, he will talk about measurement-induced phase transition and their detection in quantum simulators. Thank you.
Thank you. Hi, everyone, and let me first thank the organizers for inviting me. So today, as was mentioned, I'm going to talk about measurement-induced phase transitions and their detection by neural network decoders. So this work has been done in, is there a laser pointer? Or I just use the mouse, okay. So this work has been done in collaboration with these people, and I'm going to mainly talk about this publication that recently came out. Given time, I would say a few words about these other works, which are also about measurement-induced phase transitions. Okay. So for this audience, of course, I don't need to say much about motivating the significance of quantum simulation. However, the point that I want to highlight is that once we use these machines to engineer some many-body Hamiltonian, we should always have some ways of verifying whether the generated wave function has the properties that we were looking after. In particular, whether that wave function is in the phase of matter that we intended for. So previously, I studied this problem for systems without noise, in particular, how we can detect topological phase of matter in these systems. These are some of the works, and I would be very happy to talk about them offline. However, for this particular presentation, I'm going to talk about systems with noise, and in particular, recently discovered dynamical phase transition, which has now become famous as measurement-induced phase transitions. Okay, so why do we care about open quantum systems? So because one simple reason is that quantum simulators can be considered as open quantum systems. So when we use these machines, we start with some trivial wave function, and then we engineer some many-body quantum Hamiltonian. And then ideally, we want to generate some maybe highly entangled wave function with that. However, we always have some undesired noise because of the coupling of the system to the environment, and this creates dissipation and decoherence. So, and this can disrupt the time evolution of the system, and we may end up with something other than what we had intended for. So one way to avoid that is that we keep actively monitoring the system during its time evolution so that we make sure how the system is interacting with the environment. This way we can control the effect of the noise, and for example, we can have quantum error correcting or error mitigation schemes to suppress the effect of the noise on the system. So as physicists, we always like to study toy models. One toy model that recently has been proposed to study these kind of questions are random hybrid quantum circuits. So in these circuits, so we have some random unitary gates, but in addition to these gates, we also have some measurements in the system. So these measurements introduce some non-unitary elements of time evolution in the system. By studying these systems, we can study how entanglement behaves under noisy dynamics. So by studying these systems, people actually discovered what is now has become famous as measurement-induced phase transitions in these works. And recently, there have been experiments which have tried to realize these systems, these phase transitions for small system sizes. So The first work here was actually was done by people at UMD and Duke, and the second work was recently published by using superconducting qubits with IBM devices. So in this talk, I'm going to talk about a generic scalable method that allows us to detect this phase transition for large system sizes. And to do that, we use some basic concepts from quantum error correction. So this is the outline of my talk. I would have a brief review of entanglement entropy dynamics in closed and open systems. Then I talk about hybrid quantum circuits and some key aspects of measurement-induced phase transitions. I talk about the experimental challenge for detecting this phase transition, namely the post-selection problem. And then I talk about the way we use to tackle this challenge, namely introducing some local probes by QEC aspects. And then I explain our results, basically our setup for this neural network decoder, how we can use it for generic circuits. Then I describe some of our results for extracting the phase transition features using this method. And then I show some evidence demonstrating the scalability of our approach. And I end with some ongoing works and future directions. So as we heard yesterday, Shayan very nicely introduced entanglement entropy in closed systems. So very often we're interested to know, to quantify how a system like this system A is quantumly coupled to its environment, to its surrounding degrees of freedom. And to do that, what we do is we introduce some reduced density matrix, rho A, and then we evaluate the von Neumann entropy of that reduced density matrix. There are two limiting behaviors. One is when all the particles in subsystem A are coupled to its surrounding area, and then the entanglement entropy would be proportional to the system size. This is called the volume law behavior. Then the other limiting behavior is when only the boundary degrees of freedom in region A are coupled to its environment. This is called an area law behavior. So under unitary dynamics, generically what happens is that we can generate entanglement. And if we start, for example, with a product state with no entanglement, after a finite time, we end up entangling all the particles to each other. This is called the ballistic growth of the entanglement, that you start from some area law state, and then you end up with some volume law state. So we can ask similar questions for open systems. And before that, let me just review some terminology about open systems. So in open systems, we have a total system, and within that, we have a system that is coupled to some environment. However, because usually there are macroscopic number of degrees of freedom in the environment, we cannot keep track of how the system and the environment interact with each other. And we need to discard this kind of information in our description of the system. This discardation of the information leads to a non-unitary description for the system, for example, through the Lindblad equation for the density matrix. So we can only study the system at the level of the density matrix. And then if we want to measure some observable, we use the density matrix to make some predictions. However, if we have more resources and we're allowed to monitor how our quantum system is interacting with the environment, then the situation changes. So here, whenever the system is making an interaction with the environment, it projects the wave function of the system to one of its eigenstates. So, and depending on the number of these measurements between the system and the environment, we can have many branches. So here, this number of branches scales exponentially with the number of measurements that have been applied on the system. So we can track the time evolution of the system by the Born rule. And this way, we would have the quantum trajectory of the system. So we have the wave function of the system given these measurement outcomes that we have recorded during the time evolution of the system. And we have the wave function, so as a pure state, so we can just, if we want to measure some observable, we just evaluate its expectation value with respect to that wave function. If we end up ignoring the measurement outcomes and we just obtain the corresponding density matrix, the density matrix would be similar to the density matrix that is obtained in this way. And we end up getting the same results. So this quantum trajectory method historically was actually just introduced as a computational way of studying open quantum systems, but now in reality, we can do this kind of tracking of the trajectory of the system. So now let's consider a very simple open quantum system, namely a system with projective measurements. So this is the operator that defines our observable. These are the eigenvalues and the projections onto its eigenstates. Whenever we have a measurement, the wave function of the system is projected into one of the eigenstates. If we have a pure state and if we have a mixed state, this is how the density matrix evolves. Now, if we have uncorrelated local measurement operators, what happens is that generically we end up reducing the entanglement entropy of the system. So imagine that, like, the simplest example we can imagine is that we have a bell pair. It has a non-zero entanglement entropy if we consider the A or B qubit. But then if we measure the spin Z of particle A, then we end up going to the 0,0 state or to the 1,1 state. And what happens for the entropy is that it goes from non-zero to a non-zero value to a zero value. So in general, we can say that local projective measurements can reduce entanglement. So a many-body generalization of this concept is this toy model. So here we have these random unitary gates. In general, they can generate entanglement in the system. On the other hand, we also randomly measure some of these qubits, for example, the spin Z of these qubits after each layer of unitary gates. And the probability of the measurement of the qubits is quantified with this measurement rate P. It can be between 0 and 1. 0 is when you apply no measurement, so you have just unitary time evolution. 1 is when you end up measuring all the qubits after each unitary layer. So if we now evolve the system from some initial state, for example, a product state, we can record the measurement outcomes. Let's say we have that luxury of recording these mid-circuit measurements, and then we can label each wave function that is obtained according to these trajectories. So for the rest of the talk, I would always talk about psi as a function of the quantum trajectories. And now we can, as we said before, we can evaluate the reduced density matrix of this wave function for some subsystem, for example, the half system entanglement entropy, find the von Neumann entropy from here, and then we can average over different trajectories and over different circuit configurations. So this was a calculation that was actually done in these works, and what people found was that in these systems we can have a balanced competition between unitary and non-unitary operations in generating and destroying entanglement as a function of the measurement rate. In particular, if the measurement rate is very small, we end up with a volume law behavior where the entropy scales linearly with the system size. And if the measurement rate is, however, very large, we end up with a system that its entanglement is finite, it saturates with the system size. And in between them, there's a critical point where the entanglement entropy scales logarithmically. So, sure. Yeah, this is a good point. Yeah, so this is not for any value. So as it was shown yesterday, there's a page curve, for example, as was shown yesterday in Shoyan's talk, there's a page curve, when you increase the system, the subsystem size length, you go up to L half and then, it decreases. But the important point is that it's linear. So it scales, with the subsystem size. Yeah, thank you. Now, like other phase transitions, now you can study the scaling behavior of this quantity, the entanglement entropy. We can study its spatial and temporal behavior, and correspondingly, we can find a critical measurement rate associated with that, the dynamical scaling factor and the spatial scaling factors. So after these initial works, people have been studied this kind of phase transitions in different settings. So we can have systems at higher dimensions. We can have systems that have long range interactions. We can consider time evolutions where we have some conserved charges, whether discrete or continuous charges that are conserved in the time evolution. Then we can have, we can see this kind of entanglement transition in systems that are only consisted of measurements and which are even continuous in time. So I don't want to spend too much time, but as just an example of systems with all measurements and just and continuous in time. Here we have studied a system where such a phase transition could be observed without having any unit gate. So to do that, what we did was to introduce two dissipative channels. One was a dephasing channel, which reduces the entanglement entropy, and one was a phase locking channel that increases entanglement by coupling nearest neighbor bosons in the system. And we saw kind of a phase transition or a crossover behavior from an area law to a critical law, depending on the rate that these two channels are applied. So in this other work, we also showed that there are some relations between studying different unravelings of these open quantum systems and the complexity of the sampling. So I would be very happy to talk about this offline, but for now, let me just go to the main goal of this talk. So now what is the experimental challenge? So this is the so-called post-selection problem. As we saw whenever, when we are studying the quantum trajectory of the system, whenever we have a measurement, the trajectory of the system will branch. And the number of these branches scales exponentially with the number of measurements. So now if we have a macroscopic system, if we have many number of measurements, this would be, we would have an exponential number of these trajectories. On the other hand, the quantity that we want to measure, this trajectory average entanglement entropy, this is a nonlinear function of the density matrix, as you can see here. And so there's no like observable for that, its expectation value can generate the entanglement entropy. So because the entanglement entropy is a nonlinear function of the density matrix. So to now, if we really want to measure this quantity, the only thing that we can do is that we should generate the density matrix conditioned on the quantum trajectory, conditioned on the trajectories of the system. However, as we mentioned before, we have no control over, when we repeat this experiment, we have no control over which trajectory we end up with. These branchings are random. So in general, now the problem is that if we want to, if we want to have multiple copies of this wave function with the same trajectory, we need to repeat the experiment exponentially many number of times, so that we make sure we have the same trajectory repeated in our experiment. So this is, of course, exponentially costly. There's another exponential factor. This is due to the fact that irrespective of this post-selection problem, the trajectory dependence, when you want to measure the density matrix of a many-body system, it's exponentially costly, as it was explained yesterday by Daiwei as well. So people, however, have tried to detect this phase transition. This is still possible for small system sizes. In this experiment, people considered up to 8 qubits, and in this more recent experiment, people considered up to 14 qubits. And in this one that they had more qubits, it was actually a very resource extensive experiment. So in this work, I will try to explain a scalable way of detecting this phase transition. To do that, we need to look at this phase transition from another point of view, namely from the quantum information point of view, and in the sense that we think of these circuits as some quantum channels. These are some noisy quantum channels. There are some measurements in the system. And we want to ask, if we start with some initial state which has some entropy, how does the entropy of this state would change when it passes through this channel? So we can imagine starting from a completely mixed state, a maximally mixed state with an extensive entropy, scaling with the system size, and then evolve it under this circuit. The long-time behavior of the entropy, depending on the measurement rate, could be extensive or finite as a function of the system size. In particular, if the measurement rate is small, we end up in a phase that is still mixed. It still has some non-zero entropy. However, if the measurement rate is very large, we end up in purifying the state that was initially maximally mixed state. So, and it turns out that actually for these circuits, this critical value of the measurement rate that determines this transition from being a mixed state to a purified state, it agrees with the critical exponent and the measurement rates obtained for measurement-induced phase transitions. This perspective can also allow us to have some analogy with quantum error correcting codes, in the sense that we can think of these unitaries as some encoding gates which scramble the information throughout, non-locally throughout all the qubits in the system. We can think of the local measurements as some errors. And then this PC, the critical value of the measurement rate, is analogous to the noise threshold of a quantum error correcting code. So using this point of view, we can introduce a local probe for detecting this phase transition. In particular, let's assume a less mixed state. How do we create mixed state? We can introduce some ancillary qubits, and then if we entangle those ancillary qubits with some of the qubits in the system, we have a mixed state if we trace out over those ancillary qubits. For simplicity, just imagine that we have one ancillary qubit that is initially entangled to one of the qubits in the system, and then the rest of the qubits in the circuit are in a product state. And then it turns out that if we study the time behavior of the entanglement entropy of this reference qubit, this can provide a probe for detecting what phase we're at. In particular, in the volume law phase, it turns out that this reference qubit stays entangled to the system for exponentially long times. However, in the area law phase, it quickly disentangles from the system, and its entanglement entropy goes to 0. So by studying this entanglement entropy of the reference qubit, we can determine what phase we're at. So now the problem is reduced to a tomography problem for the denser matrix of the reference qubit, conditioned on the measurement outcomes on the circuit. So to solve this tomography problem, we just need the expectation values of the spins of the reference qubit. Just for simplicity, imagine that only one of them is non-zero, for example, sigma z. And as a simple example, just imagine that our circuit is composed of one qubit. So we have one reference qubit, one qubit in the circuit, and initially they form a bell pair like this. Now, if in our time evolution, we end up measuring the system qubit, for example, if it's +1, necessarily we know that the reference qubit should be -1. So if we have more circuits, now the problem is that instead of one measurement, there are more measurements in the circuit that may determine the state of this reference qubit. So we have now translated the problem of determining the state of the reference qubit to this mapping, a mapping from the measurement outcomes in the circuit to the state of the spin of the reference qubit. So in general, this mapping is probabilistic. It only becomes deterministic if the reference qubit is purified. If it is purified, then we deterministically can determine the state of the reference qubit. So to benchmark our approach, we used initially Clifford circuit. So here the gates in the circuit are chosen from the Clifford group. So due to a theorem by Gottesman and Neal, the time evolution of these circuits could be done efficiently by classical computers, so we can scale it up. And this allows, finding the critical exponents with a good precision. The other property of these circuits is that once the qubit is purified, it can be only along one of the XYZ axes of the blockosphere. More importantly, this purification axis only depends on the unitaries and the measurement location, and is independent of the measurement outcomes. So in these circuits, we only need to obtain one value of the spin of the qubit. So here, therefore this mapping, this decoder function becomes simpler because in the output, we only need to learn determine one spin of the qubit. So to learn this mapping, we use machine learning techniques. So machine learning techniques have been applied to many different problems. We don't need to talk much about them, like classification, regression, different problems. And our problem is a simple example of a classification problem. So we have some data, some input data. This is our input, the trajectory information, and with some outputs. So these data are labeled by the state of the spin that is measured for the reference qubit. More technically, we used an architecture which is called a convolutional neural network, which has been applied to, which has been very successful for image processing purposes. And in particular, the way we use these techniques is that we think of these measurement outcomes that have been done during the time evolution as a snapshot, as a 2D snapshots. So here we have plus minus ones for the qubits that have been measured and 0 for the qubits that are not measured at each layer. So these are the plus minus ones during the time evolution of the circuit. So this is the image that is fed to this neural net. And then after some processes, classical processes, we can determine the state of the reference qubit. And the labels are just being plus or minus 1. So more concretely, the learning protocol is as follows. So for each circuit, for each measurement rate, first of all, we need to create a number of random circuits, different circuit configuration. For each circuit configuration, we run the circuit until a short time. It actually doesn't need to scale with the system size. And then we measure the reference qubit at the end of that time evolution, for example, sigma z of it. So then we repeat this experiment many times, and we record the mid-circuit measurements and the associated labels for the spins z. So these is basically, this is our input and output. X and Y's are these are the inputs and these are the outputs. And then we use this data to train the neural net. And using that, we can obtain the probability distribution for a given trajectory. We can say when a given trajectory is given to us, then we can predict what the value of PZ, what the value of sigma z would be. This allows us to just simply find the expectation value of sigma z. And according to that, we can straightforwardly find the density matrix and the entanglement entropy. And we just need to repeat this now for different circuits. Also, because we want to study the entanglement entropy as a function of time, we need to repeat this for different times. So this time t, for example, it goes from 0 to 6 time steps in our simulations. So these are some of the results that we obtained. So the blue curve is for simulations in the volume law behavior, in the volume law phase, and the red lines are for the simulations in the area law phase. And the dashed lines are results obtained by exact simulation, and the solid lines are the results obtained by this learning protocol. So we can study the temporal and spatial properties of the entanglement entropy to find the critical exponents, Z and PC. And more technically, this can be obtained by the time dependence of SQ and its decay rate, which depends on these values of the critical exponent. So this is the results we obtained for system sizes going from 32 to 64. And this is for different measurement rates. And the results here are, in this one is for these system sizes. And here we have collapsed the data to find these critical exponents. So I don't want to go into the error analysis, just want to mention that these are the numbers we get. When considering the error bars, these agree with the results obtained from exact simulations. So of course, we can obtain better results if we consider larger circuits and we increase the time evolution of the circuit and also like the training samples. But let me just tell you how this approach is scalable. And so in particular, our decoder is based on the local information in the circuit. In particular, it turns out that when you study the entanglement entropy of this reference qubit, it only depends on the measurement outcomes. It effectively mostly depends on the measurement outcomes on a light cone that is starts from the initial location of the reference qubit. So here to demonstrate that our approach is scalable, what we did was that we started considering some boxes like this orange box. We used the data in that orange box for training our neural net. And then we started to, and then using that trained neural net, we made predictions for larger system sizes with different gates than our initial circuit that we chose. And then we kept increasing the width of this box. And what we found was that if we compare the learning efficiency using all measurements, in the circuit, or just the measurements inside the window, and call this ratio as RB. It turns out that if we increase this width of the system size, the width of this box to become equal to this width of the light cone, it turns out that the efficiencies are almost the same. So whether you use all the measurement outcomes in a very large circuit, or you just use the measurement outcomes inside that light cone. So this demonstrates that in practice this approach is scalable. Okay, so let me skip the sampling complexity of the problem. I just mentioned the result that the complexity of the problem increases not with the system size. If we use these light cone data, it doesn't increase with the system size. It only increases, it's only a function of the depth of the circuit. Okay, so I talked about Clifford circuits. Now you may ask, okay, how you may apply to more generic circuits like random Haar circuits. Here, the only difference is that instead of doing the experiment only by measuring, for example, sigma z, now we, like at the end of the time evolution for sigma z of the reference qubit, we need to repeat this for x, y, and z. So in principle, we need to train 3 neural nets, one on the x labels of the spin of the qubit, and one on the y, and one on the z. And we just repeat the same thing. So this is our input, and now these are our outputs that we use. And correspondingly, we can determine like the probability distribution given one trajectory for all x, y, and z. And then, for example, using conventional maximum likelihood methods, we can determine the entanglement entropy when all the spin expectation values are non-zero. This is a initial result we obtained for Haar circuits. Now that we are kind of repeating this, our results look better. But let me also tell you about the outlook. So the first thing is that now we are trying to actually have a collaboration with IBM where we want to observe this phase transition using this approach in the presence of noise. So the good thing about this approach is that because we're using this neural net, we're not making any assumptions about the underlying noise model in the system. So our neural net would be, once it's trained with a given device, it would just be tailored to that particular device. So it's independent of the what assumptions you're making for the error model. And another extension of this idea is that whether you can apply this to circuits with some conserved charges. For example, if you have some U1 charge, the same approach in principle is possible. Another intriguing question is that whether we can study the statmic description of these decoders that I mentioned. The other thing is that whether we can use some techniques from shadow tomography to improve the complexity, the sampling complexity of the problem, and using smaller samples. And so there's also like this kind of approach for decoding could be also thought for applying for other dynamical quantum error correcting codes. And we can use more like advanced machine learning techniques. Some of them could be even quantum machine learning techniques could be applied to this problem. And with that, let me just thank you and end my presentation. So, yes. Yes.
So actually 2 questions. The first one, with your recursive neural network approach, would it be possible to learn, let's say you take a qubit, you encode it in your circuit, you run the random circuit with the measurements. Can you use the neural network to determine the state of that qubit? Or is that too much information to try to get back out with the neural network.
Which qubit? The reference or the?
Yeah, so instead of having the ancilla that you entangle in, instead you pick one qubit and you encode some information in that qubit. Then you run the circuit, and now you want that initial information. Is there a way to adapt the neural network to get that information back?
Of that qubit in the circuit.
Yeah, exactly. So like you put one qubit in, you run the random dynamics, you want to get the qubit back out.
So if you think of this as some like label, so okay, so I assume that at the end of the circuit, you want to make some measurement on that initial qubit as well. So in our setting, so at the end of the time evolution, we measure the reference qubit. So, and this is like the mapping that we have. This is like the, the label data that we generate. So if you can do something similar to that for some, qubits in the circuit, yes, in principle, such relation should be learnable, yeah.
And just one more. So in the light cone picture, is there an intuition for why you need like that rectangle shape and it wouldn't be like the triangle shape? Because like when you have the rectangle, you're getting these measurements that are kind of outside the light cone.
That's right. No, it was just like, I use a particular like neural net architecture. That it's easier for having, the box, to have like the shape of the data to be rectangular. So this was easier, but yeah, in principle, that would improve like the learning efficiency. Yeah.
On a plot from somewhere around the middle of the talk, it looked as though when you were comparing the neural network's outputs with your ground truth of simulations, the neural network performed worse in the area law phase than in the volume law phase. Why was that?
Simply because, in the area law phase, you have more measurements in the system, and so this mapping is more complicated. So like the number of, the variables in the domain is more now. So in general, this makes it a little more complicated. Yeah.
Thanks.
You're welcome.
So I have sort of a reverse question, which is your neural network has learned something.
Right.
Can you tell us what it has learned so that you don't need the neural network anymore and the humans can understand what it's figuring out?
Yeah, I mean, that's, a very good question that you can always ask about what your neural net is actually learning. Yes, in principle, there are some approaches. In this project, we didn't do that, but for example, especially in like image processing, like applications, probably you have seen these figures that they show that, for example, this particular layer in the neural net is, for example, learning the edges, for example, in the image. Something similar would be, I think similar would be possible here as well. Yeah. Yeah. Thank you for the good question.
I guess I have a related question, which is, sometimes a neural net spits out total garbage.
Sure.
And I was curious if you have a way of quantifying that, and to what extent do you really worry about that, or is it so rare that you don't really?
No, that's a very good question. So one question in general is that, one criticism to this approach is that, we're finding the like the phase transition properties of this decoder, not the real, experiment. So, and yeah, so this is, I'm not claiming that this is like the ideal decoder that matches to that like particular phase transition. But we expect that when we increase the number of like samples, this would get better. And this is like the part that I skipped, like the sampling complexity. So we studied like for a given precision in like the prediction, how much you should feed data into that, like how many samples. So in these simulations for each circuit, for example, we ran the simulations with 5,000 samples, and that was like enough for that particular depth of the circuit.
But you might expect that the number of samples you need scales exponentially with the depth or the size.
That's exactly what we observed, yeah.
Okay.
Yeah, it scales exponentially with the depth, but is independent of the total system size.
Oh,
Hi. So when you've trained the neural network on a circuit, like what does it generalize to if you change the circuit but keep the measurement locations the same? Like,
Yeah, so in that, very good question. So I should have explained this more. So in that figure I showed here, so basically what we are doing is that we consider two circuits. One is a large circuit and one is a smaller circuit that only has the same gates and measurement location inside that box. So it's a smaller circuit, and then we train our neural net with this smaller circuit, and then we try to make predictions for this larger circuit. Then once we increase this length of this smaller circuit to become equal to the light cone, then approximately we reach the same efficiency.
any final questions? If not, let's thank the speaker again.
Thank you.